These carbocation intermediates also explain why groups like the CF3 group, that trifluoromethyl group, why they're predisposed to forming meta products and why they are deactivating towards the ring as opposed to activating. That is, they react significantly slower than benzene. Well, these 9 structures look just like they did on that previous slide, except we've got CF3 instead of the methyl group, instead of CH3. But otherwise, these are in the same order. You can see we've got ortho, para, and meta. Notice that the 2 groups they indicate and highlight here, those are the ones that are particularly stable when you have a methyl group there. Here they are particularly unstable. What they're showing with the CF3 group, this little arrow is implying that it's pulling electrons away from the ring. We say that a group like CF3 is electron withdrawing, and that destabilizes nearby positive charges. So the effect is that the very structures that are particularly stable in the toluene intermediate are particularly unstable in this example. Again, it says positive charge on a carbon-bearing CF3 group, very unstable. And so it's the ortho and para that have that particularly unstable situation. Well, with the meta, remember, that's the case where that positive charge does not ever end up at the top of the ring. And so that positive charge is never in a particularly unstable location. Again, for CF3, it is deactivating. All of its reactions are slower compared to that of benzene, but they're not all equally slow. And for the meta, it's a matter of not having any particularly unstable structures. It's the lesser of the evils, you might say. And so when we do get product by nitrating a molecule that has a CF3 group, we tend to get meta, even though it is, again, slower to react than benzene itself. It tends to avoid making much ortho and para because that would imply going through one of these particularly unstable intermediates. So again, what's good for ortho-para directing groups is just the opposite for ones that are meta-directing. And on this final slide here, we kind of summarize everything. We've got the ortho-para directing groups towards the top of the list. They are also activating, listed in order of how fast they activate that ring. Again, our standard of comparison is plain old benzene, represented by the hydrogen there in pink. And then the CF3 group, it's way at the bottom of this list. If I move a little bit, you can see it down here near the nitro group itself. Again, if those are on a ring, they tend to deactivate, slow down reactions on that ring. But again, notice meta-directing. A couple of things to point out about this. Where you see the capital R, that represents an alkyl group like methyl, ethyl, propyl. The AR here, that stands for the word aryl. That refers to situations where you have a benzene ring as a substituent off of another benzene ring. Or AR could be any substituted benzene ring. It stands for the word aryl. It's not an argon atom. What's interesting here, the halogens here are highlighted with the letter X. If I can move this table over a little bit. X stands for any of those halogens, and notice that they are deactivating a little bit slower than benzene, but yet at the same time they are ortho-para directing. Halogens can't quite make up their mind. They have pairs of electrons that are not shown on these atoms, but all halogens have 3 pairs of electrons that they can donate to the ring, much like things like the OH group I showed you earlier. But yet at the same time, halogens do pull electrons towards themselves. They are electron withdrawing, and so they have something in common with things like that CF3 group I showed you. So they are the one kind of substituent that are less reactive than benzene, but yet they do give ortho and para products predominantly. The other thing to notice is that all of these ones that are deactivating, they don't have pairs of electrons that they can donate to the ring that would stabilize that ring. That's one thing that all these groups have in common. You'll see that there are 2 groups that we might call ester groups up here towards the top, this acyl oxy. Notice the point of connection to the ring is an oxygen that has pairs of electrons to donate. So it's a lot like the OH group, a little bit higher on the list. But down here towards the bottom, what they call the ester group, that's implying that the point of connection to the ring is the carbon of that carbonyl group. It has no pairs of electrons to donate to the ring, and the nearby oxygens are pulling electrons away, making it electron withdrawing. Final thing to note that I find interesting is the NO2, a nitrogen with 2 oxygens. That's at one end of the list, way down here at the bottom. Replace those with hydrogens to get the NH2 group. At the top, you get the most strongly activating. So huge difference between having hydrogens on that nitrogen versus having oxygens. Again, at the very top, you've got a pair of electrons that nitrogen can use to stabilize that ring, much like the OH group does that I showed you earlier. NO2, though, here at the bottom, if you draw that out, the nitrogen has double bonds to the oxygens, but it does not have any free electron pairs to donate to the ring. And so it ends up being, well, the most deactivating substituent of all. When I give you a test on this, by the way, I include this table for reference, so it's really a matter of just knowing how to use the table as opposed to trying to memorize the information from it.